Hello everyone, today I want to discuss the concepts of overfitting and ideal learning in machine learning. Overfitting is a phenomenon where the model built explains examples from the training sample well, but performs relatively poorly on examples that did not participate in training, examples from the test sample. Let's start by generating synthetic data, as it's easier to see these concepts in action. We'll use the special library to create a regression problem, where we predict a target variable based on one informative feature. To make the data more realistic, we'll add some noise. This makes the task more challenging and prevents the model from learning the noise in the data. After generating the data, we'll split it into a training set and a test set. The training set will have most of the data, while the test set will have less. This ensures that our model learns general patterns rather than memorizing the training data. By visualizing the data, we can see the relationship between the feature and the target variable. Our goal is to train models that can accurately predict the target variable for new, unseen data. Let's train the decision tree model on a training sample. If you are not familiar with this model, we can discuss it later in our channel. Now let's calculate the metric of model performance quality on the training sample. We will consider the mean square error. After training, we can make predictions with this model. By calculating the mean squared error, and we can evaluate how well the model's predictions match the actual values. In this case, the metric on the training data is 0, indicating a perfect fit. This means that the model accurately predicted all the objects from the training sample. We can visualize the learned pattern by plotting the model's predictions against the actual values. The red line represents the model's learned pattern, and the blue dots represent the actual values. Now evaluate the model on the test sample, where it hasn't been trained and doesn't know the meaning of the data. While the error on the training sample was ideal at 0, indicating a perfect fit, it's crucial to assess the model's performance on unseen data. Calculating mean square error on the test sample, we find it to be much higher than on the training data. This suggests that the model is not generalizing well to new data, indicating a need for retraining. By comparing the true values to the predicted values on the test sample, we observe a significant discrepancy. While some predictions are close to the truth, others are quite far off. This inconsistency indicates that the model is not performing well on the test data. Visualizing the learned pattern on the test sample, we see that the model's law represented by the red line does not align well with the test points and their predictions. The red dots show the model's predictions, which are notably different from the actual test values. Finally, our model did not search for the law that all the data in this task follow, but only memorized the objects from training. This is overfitting. Here we will have a perfect quality metric on the training sample, while on the test sample the metric will be bad. Let us now look at underfitting, where the model is so simple that it cannot remember anything, neither the training sample nor the data as a whole. Firstly, explore the training of a decision tree model with a maximum depth parameter set to 1. This means that the tree will only ask one question during training, leading to a simplified tree structure. Let's calculate the mean square error. The resulting high value of the metric means that the model is not doing well and has failed to memorize the training sample. Our predictions are not even close to the true values. Let's visualize the law learned by the decision tree model. With a maximum depth of 1, the model only makes one split based on a single question. However, this simplistic model fails to capture the complexities of the data. It does not attempt to match all the true values and merely creates a step function. This indicates a lack of effort to understand the underlying patterns in the data. Evaluating the model on the test sample, we find the root mean square error to be 639, which is lower than on the training sample but still significant. This suggests that the model's learnability is poor, as it struggles to generalize to new data. Let's finally train our model normally, when it will not memorize the training sample, but when it will understand the data structure of our problem. and take the decision tree model again and give it parameters that are more or less suitable for this problem. Let's compute the mean squared error. The metric is not 0, but it is not huge either, which means that the model is doing well and has not started to memorize the training sample. Also, somewhere the predictions are close to true, somewhere quite far away. And also visualize the pattern learned by the decision tree model. I am glad that the model did not start building the law that passes through all points of the training sample, so it went further and did not start memorizing the training set, but tries to catch the general regularity of the data. Additionally, look at the test. The quality of metric is not 0, but it is not huge either. It is larger than the training one, but it is not so bad, because our data is very noisy, and there are few of them. As we see, test predictions fluctuate around the true values. The red line does not go through the test points, but it goes somewhere in the neighborhood of the true values, which means that the model tried to remember the basic meaning of the data and tried to recover this dependence between X and Y. This shows more or less adequate training, and there will be a pretty good quality metric on the training sample, as well as on the test sample. In summary, overfitting occurs when our model performs poorly on both the training and test data. Underfitting happens when the model performs poorly even on the training data. Good, ideal training is achieved when the model understands the general essence of the data. However, if the model starts to find patterns that shouldn't be there, it indicates overfitting. Today we've covered 3 key states in machine learning: underfitting, normal learning, and overfitting. In the description, I've included a link for you to run checks and gain a deeper understanding of overfitting and underfitting. Best of luck on your machine learning journey, and may everyone achieve success.